The purpose of the X-ray generator and its controls is to convert available electrical power into precise X-rays, and the peak voltage is anywhere between 50 to 150, so soft to hard X-rays production. So for soft you need 50 kVp subscript P, and then for 150 and more would be for hard X-rays. Now that's not the same. Hard X-rays are not the same as hardened X-rays. Hardening of the X-ray beam is the introduction of aluminium. That's more akin to collimation. So one circuit is for producing the voltage. The other is about this circuit drives the direct current, and the other circuit is to regulate the current flow. And the radiation passing through the patients measured in feedback circuits. There's feedback signals used to regulate the output of the generator in response to changes in patient size and position, with reference to gantry. And the generator construction is I can best explain it through an algorithmic diagram, but for reading purposes, it's linked to the national grid. It's deriving around about anywhere between 110 to 440 volts. In my experience, it's around about 400 volts. This is usually supplied as a three-phase forward bias rectifier, 60 hertz frequency, C equals 1 over 2 pi FC. And then a hospital wiring for the X-ray generators needs some special attention in terms of insulation, compounding, and protective circuitry. So in case if any they need bigger fuses. And the minimum acceptable power rating of an interventional radiographic generator is around about 50 kilowatts, as in power unit of power. So that's 50,000 joules per second. And to get an impression of the magnitude of this power level, a heavy-duty hairdryer uses about 1,000 joules per second. So isolated generator power lines protect the remainder of the hospital from voltage transients caused by radiographic exposures. So what we learn here now is the microcircuitry. So there's a bit of a curtain between, there's slight separation and specialization between the within the hospital electrical transmission circuitry. The wires for they go into the radiographic department are slightly sheltered, and they are kept slightly away from the main hospital electricity supply, and the less power is needed to supply mobile fluoroscopic generators such as those found in operating room. But nonetheless, there is a degree of separation. So fluoroscopic performance of such systems is quite acceptable. Their radiographic capabilities are significantly below that of fixed installations. So the block diagram of an X-ray imaging system is through an algorithmic diagram. So you've got the generator, which is the transformer taken in, and then the X-ray tube, X-ray gun, and then the X-ray is being produced here. The patient's laying down here, and then the image receptor is recording everything, and then sending it back to the feedback loop to moderate and modulate the amount of radiation being pushed out of the generator into the X-ray tube, by the X-ray tube onto the patient. So mobile systems are used for bedside radiography, and they derive the energy from onboard batteries. The batteries store enough energy to drive the system around the hospital and produce the relatively small number of radiographs required between recharges. The X-ray voltage needed for proper imaging from 50,000 to 150,000 volts, ideally. The tube receives a constant, non-fluctuating voltage during the exposure. The modern generators start the task by converting the energy flow to DC. This is done for engineering reasons. This energy derives a power oscillator. These oscillators are operated in the 500 to 5000 hertz range, 0.5 to 5 kilohertz range, and the operating sound made by the generator tells you the frequency. So audio frequencies permit the use of smaller high voltage transformers than those required at the power of line frequency of 60 hertz. Um, Audio frequencies permit the use of smaller high voltage transformers than those required at the power line frequency of 60 hertz. Rectifiers are placed between the output of the high voltage transformer and the X-ray tube, and the devices convert the transformer's AC output to DC. I think it's best, what it's telling you here is best explained to this diagram, where you get the AC current from the national grid, and it's converted to DC here by the hospital, and then it's sent to the oscillator where it converts low voltage AC to audio frequency, and that audio frequency goes to the transformer to step up the voltage to X-ray levels. And then the rectifiers, the forward bias rectifiers, prevent the backflow of current, and they induce a sense of efficacy and efficiency in the apparatus, and then they push the current and the voltage forward into the X-ray tube, and then the patient gets the X-ray dosage, and then it gets analyzed and imaged by the receptors, and then there's a feedback loop, and then the feedback loop goes all the way to the generator. So the time of X-ray production is controlled by applying and removing the power to the X-ray tube. This is done using electronic switches in the oscillator, high voltage tank, or by use of the grid in the X-ray tube. Electronic control of the oscillator determines the voltage applied to the X-ray tube. Control signals are supplied by the system controller, high voltage tank, and automatic brightness control system. The system controller signals establish the initial operating factors. The instruments in the HVTM HVT monitor the voltage and the current. Signals from these instruments are used in feedback circuits to maintain required operating conditions, so it's slightly homeostatic. The multitude of sensors and feedback control provides closed-loop control of all critical operating parameters. These components provide stable long-term system performance. The intervals needed between routine calibrations can be safely extended relative to previous generations of open-loop systems. Of course, maintenance, quality control, measurement, and calibration are needed when smoke comes out of the system or an X-ray tube, or the other major component is replaced, or whenever a major component is replaced. Okay, so the automatic brightness control is here. The field of view, collimator position, limits of measuring field. The ABC system measures the peak or average brightness of the portion of the image inside the measuring field. Here, the X-ray beam totally illuminates the measuring field. Some systems take a simple average of the brightness, amplitude, i.e., and in the measuring field. So other systems are designed to search for maximum brightness. All systems perform equally well when the X-ray field is larger than the measuring field, and a relatively homogeneous portion of the patient is being exposed as a function of time. The figure we've seen here is good, but it's talking about this figure now. The relationship between measuring fields and X-ray fields. Large measuring and X-ray fields average a large fraction of the patient's anatomy. A large measuring and small X-ray fields produce too low an average reading. A small measuring field averages only a small portion of the patient's anatomy. This can give a false reading, false positive, false negative. A small measuring field minimizes the effect of measuring outside the X-ray field. So we have to have a balance between the measuring field and X-ray field. So conditions where X-ray field is bigger than the measuring field, or where measuring field is bigger than the X-ray field, or where X-ray field is equal to the measuring field. All of these 3-4 conditions need to be managed and in an astute manner. so that the patient gets the best combination of dose and accuracy and least amount of scatter, so that the image produced is extremely accurate and facilitates um, diagnostic precision. So this figure that I just showed you illustrates combinations of measuring field and X-ray field sizes. Such a combination provides a signal that represents the average transmission through. So the figure, this one here, would provide a signal that represents the average transmission through a large portion of the patient's anatomy. The B would show X-ray field has collimated to less than the measuring field. The unirradiated portion of the measuring field lowers the average. This results in, sorry, there should have been in, it should have mentioned. This results in too much X-ray output. Because of a hyper bright image, as the system attempts to image outside the collimators. A small measuring field in C and D produces the correct output if it overlies an average density tissue, like muscle. It'll produce too much output if the measuring field's over the bone, and insufficient output if measuring over the lungs. The relationship between measuring field size, shape, and average technique is not confined to fluoroscopy. Such similar considerations apply to measuring the brightness in photographic scenes. The ability to match a measuring technique to particular tasks has been improved, and these improvements lead to an increased ability to optically dissect the scene. The radiologists and the operator needs to intervene, and in most cases, and to select the appropriate measuring program, i.e. the software. So now we'll talk about the exposure time control. The system is often switched on and off at a generator level, and the tube and the generator are connected by high voltage cables. These cables store electrical charge. When the voltage is applied, the charge continues to supply energy to X-ray tube after the switch is opened, and this will prolong the exposure time for a certain amount. The cable discharge time is prolonged when the cables are long and the X-ray tube current is low. This leads to excessive motion unsharpness, lower resolution. Some X-ray tubes employ a biased cathode to electrically switch the current on and off. For historical reasons, this is called grid switching. When its operating parameters are compatible with the required radiographic technique, grid switching eliminates the problem of cable discharge. The X-ray tube converts electrical energy into X-rays. Okay, basic physical factors that make this is a very inefficient process, very inefficient, like the incandescent light bulb. Less than 1% of the electrical energy is converted to X-rays. The remaining is heat, and tubes are constructed to handle this waste heat without damage. So much of the aggravation about system-imposed delays is due to time needed for heat management. Modern tubes are capable of handling several times as much heat as those of the early 90s. These tubes can deliver significantly more radiation without overload. This was possible a decade or so ago. Then it was possible a decade or so ago. The essential elements of the medium power X-ray tubes will be shown in figure 4.5. The vacuum tube starter cooling components are contained in the protective housing. Oil filling contributes to the system's electrical insulation, as well as participating in the tube's heat management process. The housing protects the patients and staff from electrical shock by providing a grounded outer shield. The lead absorbs stray radiation going in directions other than those intended to be the useful beam. This is a typical X-ray tube. I've held one or two in hand, and I know what they look like. The bearings, rotor bearings, anode, the rotating anode, the target track, beam window filaments, cathode cup, the vacuum envelope, cathode connections. So the tube's vacuum envelope provides the necessary high vacuum environment for remaining components. Most vacuum, so basically this is the target track. and the tubes vacuum envelope provides the necessary high vacuum environment for remaining components. The many vacuum envelopes are made of metal instead of glass. Electrons are generated in the hot filament by process of thermionic emission. Tube current is controlled by adjusting the filament temperature. This can take a few seconds because this is thermal process. As previously indicated, elements in a tube current circuit provide the feedback needed to stabilize the tube current. Filament maintained at a lowest standby temperature, and this is an important factor in tube life. So the electrons that constitute the tube current in milliamps are electrostatically directed to the focal spot by the cathode cup. Most X-ray tubes have two differently sized filaments in two cathode cups. Heating the appropriate filament determines whether the large or small focal spots active. The target of most X-ray tubes is tungsten. The combination of a high melting point 3400 degrees and high atomic number 74 makes the best choice for most situations, i.e. tungsten. A small percentage of rhenium is usually alloyed with tungsten to maintain smoothness of the target. This alloy provides a more consistent X-ray output over the tube's life. The body of anode is often made of molybdenum or graphite, as I mentioned earlier, and the materials provide good thermal conductivity and a large heat storage capability. Electrical and thermal safety circuits limit X-ray tube operation to protect tube elements from thermal damage. Even tungsten doesn't always stand up to the rigors of high-power radiography without melting. Several techniques are used to spread the energy in the electron beam over enough target material to avoid meltdowns, shown, for example, in figure 4.8 over the next page. I don't know why this book can't keep figures and the text on the same page. The first method of spreading out the beam is called the line focus principle. The central, in the figure that's not available on this page due to poor organization, the central ray of X-ray beam is perpendicular to the electron stream. The focal spot on the anode is at an angle to the central ray. Decreasing this angle produces the same square effective focal spot using a larger rectangular physical focus. This increases the tube rating. This is obviously a marriage where the quality suffers, and decreasing the anode angle decreases the maximum available size of the X-ray field. In addition, the X-ray fields produced by smaller angle anodes are less homogeneous than those produced by larger angle anodes normally. This is not normally in the sense of perpendicular, but normally as in like the convention. This is called the Heel effect. Non-uniformity may be an important factor in video densitometric analysis. This is the image 4.7, the cathode assembly with filaments for large and small focal points. The inert is the upright. The insert is the upright. In the upright is a pinhole photograph of an actual spot. So it's a very small, obviously, it's a small component of the X-ray tube. Most tubes, I mean, here it's talking about the rotating anode, how it increases the efficacy of X-ray production and focus on the target. Moving cool target material through the electron beam enables much higher power levels than possible with a stationary anode, because the stationary anode may get heated far more quicker. So increasing the anode's diametric dimensions increases the track length, and therefore the short-term tube ratings. So anode rotation is accomplished by EM linkage. And the motive, the power from the stator coil located outside the vacuum envelope to a rotator coil located on the anode's shaft. Typical operating speeds range from 3,000 to 10,000 RPM. And obviously you have to support the rotor. If you wouldn't, it will fall off. Conventional tubes use ball bearings. Ball bearings are a universal component used in automobiles and in many other aspects of linkage of mechanics, so you have to have that. And then you move on to this page where it's showing you figure 4.8, the X-ray tube's damaged rotating anode because of heating, internal resistance, and melting. And you can see the line focus principle is used in addition with the rotating anode, so that even if it, so the accuracy at higher powers can be maintained. So this talks about focal track length and single exposure focal spot ratings, and the ratings for any given voltage decrease as the exposure time is increased because of increasing target temperature, melting problems, and internal resistance and quantum problems. Specialized tables are used to determine the safe ratings for rapid sequence exposures. And now we'll talk about, so this is a graph about the cooling curves. The cooling curve is interacting with the power rated heating curves, and so it's interacting with all the four curves, and they seem to plateau at 500. After 2 minutes they seem to begin to plateau, so that's good. That's a positive thing that they're plateauing, but it takes about 3-4 minutes for it to come down from 85 to 30 degrees, 85 to 25 degrees, about 60 degrees in 3 minutes. So that's 20 degrees per minute gradient, negative temperature coefficient gradient, NTC. So X-ray beam collimators minimizing field size by collimating the beam is a rare example of simultaneous improvement in image quality and a decrease of radiation risk. X-rays are emitted isotropically, i.e. in all directions from the focal spot. A port in the lead-shielded tube housing defines the maximum size of the X-ray beam. Tube ports are manufactured to fully irradiate the largest image receptor at the shortest working distance. In most circumstances, the uncollimated beam is larger than the image receptor. This is undesirable for reasons of image quality and radiation protection point of view. So one should only use radiation in amounts that benefit the patient with the medical Hippocratic oath of do no harm or do least harm. Using an X-ray beam that is much larger than the image receptors are wasteful of radiation and produces unnecessary risk. Subject contrast is maximized and the radiation risk to both patient and the staff is minimized by collimating and hardening the X-ray beams. So the amount of scattered radiation produced is the patient increases with field size. Increased scatter decreases image contrast. Staff and patient radiation risks also increase with beam size. Adjustable collimators are provided to limit the radiation beam to at least the size of the active image receptor and ideally to the size of the region of immediate clinical interest. So that's that. This is what the diagrams are talking about. And, the aperture, plate limit, and the emitted beam size for the square focal spot is shown here. And I know this is slightly complex, but you have to read through it to be able to understand. And you have to make notes and mathematical symbolic notes as you go along the chapter. Because we know that X-ray tubes produce a significant amount of off-focus radiation, scatter, and soft radiation, Bremsstrahlung and Kerma. Such radiation is produced when electrons are scattered inside the X-ray tube, eventually producing X-rays by interacting elsewhere in the tube. So this is unfocused, extra unwanted radiation. So collimators like copper anodes or copper lenses, they either fix or variate it, and fixed collimators have no place in modern interventional systems. Variable collimators are required these days to adapt to changes in image receptors field of view. So these are lenses made of metal. Now, just to summarize, image intensity measurements and closed-loop control circuits provide consistent imaging performance. If you had to write something in the exam, I think these 3 sentences would do you a world of good. Almost all of the electrical energy is applied to an X-ray tube, and when it's converted into heat around about 99%. The tube design is focused on safely handling this heat. I hope in future more efficient X-ray tubes shall come into existence. I don't know why they aren't, why they haven't been able to, because but you can these days modulate, hypermodulate through nanocircuitry. but I don't know why that's missing. Collimators control the size and shape of X-ray beam. One should never irradiate objects that are not within the active field of view of the image receptor. So that concludes the chapter number 4 for Interventional Fluoroscopy by Stephen Balter, PhD, and then it's the physics, technology, and safety of fluoroscopy only. Fluoroscopy is the word given to video imaging, videography. So basically, you're seeing a video as you are going through the patient. So this is what fluoroscopy stands for. It's not imaging. It's not CT scan. It's not a scan. It's not a fixed stationary scan. It's a video, and you can take pictures of that video, and that's why the software takes high resolution pictures of the video that are later stored as images and a video file and the image files, and that are then printed out on blue plastic, the blue polymers, and then they are examined by the radiologists. So I hope you learned something today. I apologize for the lack of vocal enthusiasm. I tried my best, but it was quite a lot to read at this volume and pace, and I hope you learned something today. And that was the chapter 4 of interventional fluoroscopy of this book. So thank you very much. I hope you had a lovely day. If you've got any questions, please post them down below in the comment section, and I'll try my best to answer them. Thank you. Take care. Bye now.